Hi, I'm Bruce again, and welcome to my Rocky Mountain lab. Today we're looking at a Analogic AN3100. It's a 5-decade DC voltage standard with 4 decimal places. You can dial in anything from 100 microvolts up to 11.111 volts and in 100 microvolt steps. Um, Interesting thing about this unit is once it was repaired and tested and guaranteed to be in working condition, I went ahead and modified it utilizing assistance from the ex-chief engineer of Analogic, who was around at the time this was developed, and was able to implement an overall zero offset scheme. So this unit's been modified to provide zero offset, and it does so right down to the microvolt level. As you can see, we've got 0 microvolts offset right now, plus or minus 1. And what it does for us is that it effectively gives us an extra decade of accuracy, because now in the tens of microvolts decimal place, we're going to get a 0. And we'll see that as we do the testing. Okay, well, it's been about 3 hours, and as we can see by the meter, we've settled out to approximately 0 plus or minus 1 microvolt. So we're ready to begin the testing on this unit. So bear with me and we'll get started. All right, we have the Analogic 3100 adjusted for 0 offset, and right now we're set at 10 volts using the 1 volt switch, step switch, and we are reading 9.9999, 8 or 9. Let's give it the doubt. We'll say it's all 9s. So that's 9 point and then 5 decimal places of 9s. But the unit only has 4 decimal places there, so that's a good point that I want to point out here, is that I'm going to show you in the end that we're getting 5 digits of accuracy out of a 4-digit unit, where the last digit, as we get down to the smaller ranges, you're going to see that it's basically 0, except for whatever errors there are in the switches and resistors of their different ranges, but it'll all be within the specifications of the unit. So, okay, we're going to go from 10 to 9. So we've got 9.4 zeros and a 1, well, flashing between all zeros. Yeah, we just settled out. 9 and all zeros, 5 zeros. Let's go to 8. 7 and 5 nines. Yeah. 7 volts. It looks like 7 and 4 zeros and a 1, I'm going to call it. 6. We've got 5, 4 nines, and a 6. 5 volts. 4, 4 nines, and an 8 or a 9. We'll call it an 8. 4. Okay. 4, 4 zeros and a 2. 3 volts. 3 and 5 zeros. 2 volts. 2, 4 zeros and a 2. 1 volt. We've got 4 9s and a 7 or an 8. I'm going to call it an 8. I think it's more 8 than 7. And then back to 0. Okay, let's go to the second switch here, starting with 10. So that would be 1 volt, and we are getting 4 zeros and a 2. Okay, let's go to 0.9 volts. We got 0.93 zeros and a 2. 0.8 volts, 0.83 zeros and a 2. Bouncing between 1 and 2. 0.7 volts, we got 0.73 zeros and a 2. 0.6 volts, 0.63 zeros and a 1. 0.5 volts, 0.53 zeros and a 1. 0.4 volts, 0.44 zeros. 0.3 volts, 0.34 zeros. 0.2 volts, 0.2 and 4 zeros. 0.1 volts, we got 0.1 and 4 zeros. And then 0, we're still holding our 0. We're going to go to the 0.01, the 100th volt. We're going to go up to 10, which would make that 0.1 volts. And we are getting 0.1 and 4 zeros. All right, 0.09 volts. We're getting 0.09 and 3 zeros. 0.08 and 3 zeros. 0.07. 0.07 and 3 zeros. 0.06. I'd say we're getting 0.05 and 3 nines. 0.05, we're getting 0.04 and 3 nines. 0.04, we're getting 0.04 and 3 zeros. 0.03 volts, 0.03 and 3 zeros. 0.02 volts, 0.02 and 3 zeros. 0.01 volt, we're getting 0.01 and 3 zeros. And then back to 0 again, and we're still holding. Alright, so we go to the millivolt selector. Let's take ourselves up to 10 millivolts, which would be 0.01 volt. And we are getting 0.01 and 3 zeros, or we're getting 0.009 and 2 nines. Which is it? Kind of in between. So forget me, I'm going to go ahead and call it 0.01 and 3 zeros. Let's go to 0.009, that's 9 millivolts. We're getting 0.009 and 2 zeros, or 0.00899. It's flashing between the two, so it's something higher than 899 and possibly less than 900. But I'm going to call it 9 millivolts. 8 millivolts, we got 0.00800. 7 millivolts, we got 0.00700. 6 millivolts, 0.00600. 5 millivolts, 0.00500. 4 millivolts, 0.00400, possibly 399. We're something higher than 399. But we'll call it 399. So that's 3 millivolts. We get 0.00300. 2 millivolts, 0.00200. 1 millivolt, 0.00100. Back to 0. Still holding. And then finally the fourth decimal place, so we are 0.1 millivolt range switch. We're going up to 0.910. So this would be one millivolt, and we are getting 1 millivolt with, so 00100 going to 0.9 millivolts. We got 0.89 to 0.9 millivolts. I'm going to call it 9.9. 0.8 millivolts, we got 0.80, 0.7 millivolts, 0.70, 0.6 millivolts, 0.60, 5.5 millivolts, we got 0.50, 0.4 millivolts, we got 0.40, 0.3 millivolts, we got 0.30, 0.2 millivolts, we got 0.20, and 0.1 millivolts, we got 0.10, keeps flashing to 0.1, so I'm going to take it. And then 0 itself, we are flashing between 0 and a -1, so that last count's got us there. But we've got the readings. We're going to go ahead and graph them and see what the results tell us. Huh? Okay, so we've graphed the results of the testing on the AN3100. This is serial number 4572. And it's the same copy that you'll see in the photograph on the ad for the unit. All of the results are listed in black under the decades. All the expected results are in blue. And then the error is in red below here. So let's try and zero in a little here on the error. I'm going to shift her up and make it easier to see. Okay. That should be a little better. So our expected error, according to the original specifications for the 4 decimal unit, was 0.005 plus or minus 50 millivolts, or microvolts, excuse me. So 0.005 would be the third position. We've got 0.0001 on the first measurement here. So as we go down the list, we see we hit 0.002, 0.003 approximately. Okay, so as you can see, about the worst case here in this part of the screen is 0.0167 and 0.02%, both negative. Those were due to, in the case of the 0.0167, we were trying to read 0.06 volts. We got 0.05 and 3 nines. So a 10 microvolt error in the reading caused a 0.0167% percent of error. So if you were to add plus or minus 50 microvolts, let's say plus 50, that 10 microvolts is overwritten by 40 additional, up to 40 additional microvolts. So we're well within the specification for that reading, and the same thing goes for the 0.05 and the next one. Again, we were 10 microvolts off in the reading. We could easily get that back from that plus or minus 50 microvolt addendum to their general specification of 0.005%. Okay, so then, whereas we get 0 all the way down to this point here, we see we're a negative 0.25%. Well, let's see, that's 1, 2, 3, 4, 5 readings up. So 1, 2, 3, 4, 5 readings up. We were trying to read 0.004 volts, so that's 4 millivolts. So we got a reading of 0.00399. So we were, again, 10 microvolts off. If you were to add up to 50 microvolts were allowed, so we easily got 10 in there. So we still hit our specification without being in any trouble. And that was the only, and from that point on, in the third and fourth decades, we had all zeros for error. And we had zeros going down to a fifth decimal place. So as we see here, we're reading 5 decimal places, 0.00100, and we got it. And for 0.00090, we got exactly 90, and so on, right down to the 0 reading. So we picked up a 5th decimal place. You can't adjust the 5th decimal place in value other than you can adjust the 4th decimal place, so you have 10 values that are going to be affected by it. So there you go. Beautiful unit, stable, seems to be repetitive. I've done this now 4 different times on the same unit, and I've come up with the same results. So happy bidding, and thank you for listening. Bye.